Teaching e to the x, math for physics. There are three basic equations that have variable exponents. We know most of these from the first one, which would be called exponential decay. And we usually use this as a half-life. So basically in this thing, we have a chain of probability as the material, the base material, B here, and over time, we now have an exponent of time versus the half-life. And that basically decreases the amount as they interactively reduce by the material. Similarly, we have what's called a Gaussian distribution. That Gaussian distribution uses mu, which is the median, so you're halfway through between the two options, and the sigma here, which is the deviation. And so by doing this one, the 1/2 is in the exponent, so e to the 1/2 times x minus mu over sigma. The third option is the regular e to the x that's presented in many equations in physics. And this is the one we're going to concentrate on. The important thing to know is that that first one has a 1/2 in it. The second one has a 1/2 in it. And the third one has a hidden 1/2. And that's partially why students have a difficulty understanding e to the x equations. Now, what is Euler's number, E? Well, it's not really statistical. It is a defined chain of interactions of velocity and reactions. The most important part is not e to the x, but down here, this hyperbolic sign of x. That's sine h of x. And that is equal to half by e to the x over 2, but half by the inverse, e to the minus x over 2. And there's a reason why I'm going to convert this every time you see a standard e to the x. You're going to have to convert this. So this e to the x, I always want to convert into e to the x plus 1 over e to the x, or e to the minus x, as you saw. That conversion then makes them interactive and things. Let's talk about how that is, and that combination, hyperbolic sign. The hyperbolic sign is as if you have a lattice, a big plane, and say an electron is coming in this green path, and that's a parabola. So it comes in and interactively, with that distance going down, the acceleration changes, reduces, until it either gets repelled through or it passes through and becomes this red sort of S-curve, which is a deflection. Okay? This is exactly the sort of thing as a photon passing a planet or a star, which is exactly what Einstein got his Nobel Prize for describing, using this e to the x. But really hidden in that was this e to the x plus 1 over e to the x. This is the degrees of freedom that you need to make this work. So the secret to the hyperbolic sign is that it's interactive and derivative. And so this is the final concept. That green parabola, or the deflection parabola, inverted, the black, is where the force and the acceleration are interactive. As you get closer to that plane, it becomes more repulsive, and then as you are either thrown away or pass through it, it becomes less, but there is some sort of interaction. This is part of the basic physics stacks: position, speed, and acceleration. and that you have two parts of it that are interactive. Well, that's really a challenge for many people because an interactive stack means that you've got units of measure that sort of are both steps at the same time. So now you've got xy times k, or y equals k over x. That is the definition, and if you ever see those xy's multiplications, that probably means it's an interactive thing. Now, the secret, which I said was that e to the x has a hidden 1/2, is that if you restate that in the form of a Gaussian with a 1/2 in the exponent, so we're taking the effectively square root of it, if you take the derivative of it, that's minus 1/2. Well, that's the inverse that we just talked about. So the math secret is that only equations that have x to the 1/2, and there's this nice special number called Euler's number that does this perfectly, then it becomes an interactive state. But it's not e to the x. It is always two components getting you acceleration and velocity as interactive. So how does this work? Okay, now if I'm going to take the position over time, we're basically going to take the position with some velocity function over time and some acceleration over time. And that really is the derivative of over position and the second derivative. Now, if you do this, then the way I'm thinking, you have some base to the 3/2 as its initial position. You have then the derivative of that, which will throw that equation down as a constant, the 3/2, and then you get the equation segment for velocity as a function of velocity as b to the 1/2 x. Good, that's the 1/2. Then if I take the derivative of that again to find out what the acceleration is, that's going to be that 1 over 3/2, but with another 1/2 coming from the distribution, and now I'm going to get b base to the minus 1/2 x. Okay, now I have an interactive between those two and a function of time for all three. Now, you think this is very strange. So velocity plus acceleration then becomes the sum of those two, and that equals 0. This is a tension, this interactive locking of those two steps. And you now have an equation. Strangely enough, if you have this 3/2 and this 1/2, you get 4/3 in that other equation. Now, if I look at those derivatives, and I'm going to focus just on the two steps, not on the full equation, the velocity is the derivative of that. The acceleration is the double derivative. And so now, when I'm comparing those two, I basically get 4/3. And that 4/3 is acceleration function times velocity functions equals some constant. Fully interactive, fully directly interactive. Now, think of this as a pendulum. There's a pendulum sort of because, as we know from other interactives, you don't have to stay at the beginning. A basic pendulum is an inverse reaction of acceleration and velocity. So how does this work? So there's an invisible accumulator. That's the functions that we call imaginary I, although, as you know, I hate that wording. It's invisible. Now, we get this calculation. So in the end, I'm going to now take all of the EX functions, and we're going to think about this strange thing where velocity in the bottom here, say event set 2, is an inverse from velocity to acceleration. But then we also have the two particles or two objects interacting, and they also have this sort of inverse relationship. Or we have two time slots. And so basically it's some inverse to inverse, inverse to inverse. And so every time you see an e to the x equation, we're going to convert it to an e to the 1/2 x plus e to the minus 1/2 x, which of course is also the inverse.